Good morning, Tony. All right, guys, so I've got the bell work on the board. It's going to be over there now because I realized putting it here wasn't too smart since I'm sitting right in front of it. So there's your bell work. We're going to have the rest of the class on Zoom today, hopefully, maybe. Let's get okay. Hope this works. You got 2 minutes. Yeah. Everyone else has 5, just you. Yeah?
It didn't go as I thought.
What do you mean by that? Ankle isn't doing well?
It's been swollen.
Yeah.
So my he's gonna do extra exercises with me.
Yeah.
But he said if it's close in next week, it'll clear me.
Yes. I've been doing PT every single day, so.
It's gonna get better eventually. Your voice can still be recorded. The voice of other participant. For 1 and 2, oh, I have it up there too. Just leave the answer in. Leave the answer in exponential form. How's it going, David? How am I disconnected already? Yes, David.
Do you, if I write it down on paper and then just show it on my screen, is that what you want me to do for bell work?
So I'm going to go over it. So just as you're doing the bell work, I'll go over it with you. And then if you have it wrong or you have a question about it, ask me. But if you got it right and you understand it, just go ahead and leave it be.
Just keep on listening to the class or whatever. Okay.
Yeah, so I'll go over it in about.
No, this is just going to be like. Okay. And this is just going to be like I'm regularly in class. I just listen to your lesson and take down notes.
Yeah, exactly.
Okay.
And again, if
Right on,
this will be my first time doing it, so if something's not working for you or if you need anything, just let me know. But if not, you don't have to confirm with me anything because it's going to be hard to keep up with both. But again, if you have any trouble, feel free to ask me at any time.
Alrighty, right on.
Okay. It's gonna be fun. Hoping my Zoom works the whole time. David's Galaxy.
Really quickly, I'm gonna go check on Infinite Campus so I get my attendance for your class.
Oh gosh. Morning, Seth. Golly. Oh, geez. Computer's already crashed. Oh, I'm back. All right. Okay, good. There we go, Aiden.
Yeah, you're still sitting up there.
So we'll see what happens to Zoom. It's like, it'll draft. Yeah, it's open.
Aiden was here.
finished with my bell work. I'm going to check in for Infinite Campus.
All right. Joey's here. Shyla. Tommy. Cooper. Ben. Zach. I've got David and Isaiah in the room. Alrighty. So David, Isaiah, if you guys ever can't hear me or have questions, just raise your hand. But if it's working, you're getting what's going down, just let me know. Or don't let me know. But if it's not working, you don't know what's going on, let me know, and I'll try to answer your questions. All right? Okay, for you guys, sometimes I'm talking to the computer. We got some people on Zoom. There's Aiden back here. All right, so I'll give you about another minute or two for the bell work. So there we are, Branson. So for 1 and 2, you can see your answer in the exponent form. So if you remember the rules for those, should be fairly quick. And then 3, A and B, and we haven't exactly seen B before, but if you use what you know about square root and cube root and stuff, you might be able to figure it out. Because if it's a cube root of 27, you're looking for what raised to the third power. If it's the fourth root of something, then you're going to be looking for the fourth power. So, hello, Christopher. Christopher, there he is. All right, so let's go over this. So number 1, we talked about these with the exponents that are multiplying with like bases. Since they both have a base of 3 and they're multiplying, number 1, it would look like this: 3, 2 plus 4 to get your answer of 3 to the 6th power. So we're going to start writing it out like that and showing that you're doing the process. So if you don't have that, just go ahead and make that little note. Because again, we're going to have sometimes where one of these numbers could be a variable and you might not be able to add it, so you'd have to leave it like that. And I'll show you what that means at some point or another. But the biggest thing to know is that we're multiplying. They have like bases, so we just add their exponents. And in this case, we can do 2 plus 4 to get 3 to the 6th power. So that'd be your answer. Number 2, we have 4 to the 8th divided by 4 cubed. So this same thing except for opposite. So we would do 4 to the 8th minus 3 to get our answer of 4 to the 5th power. So this time they were dividing. So since they were dividing, we just do the first one minus the second one. So the one being divided minus the one going into it. And you get 4 to the 5th power. And again, you get like this, unless it's something I tell you to solve out, or if it's something simple like 3 squared, you can do it. But if it's 3 to the 6th, 4 to the 5th, you can just leave it in that form. All right, tree. We got part A, the cube root of 27. So you're just looking for the number raised to the 3rd power to equal 27, and that would just be 3. And if you wanted to show work, it could be 3 cubed equals 27, and that's your work. Because again, this number right here, the one kind of to the left of the radical, that's the radical, this little squiggly line, that's what power we need for our number. So 3 cubed equals 27, so the answer is 3. So going off that same logic, the fourth root of 81, we're looking for what number raised to the fourth power is going to equal 81. Well, in this case, it's also 3. Because if you do 3 to the fourth, you get 81. So the fourth root of 81, or what number when raised to the fourth power will equal 81, and that would be 3. Okay. Any questions over any of those? My Zoomers, you able to hear me all right?
Yes, sir.
Yes.
All right, I saw you unmute, so I'm just gonna assume you said yes for a second. All right, if not, again, just raise your hand, tell me whatever, and we'll get it figured out. Cool. Let's get going. So hang on to that bell work. Hopefully you still have the sheet from last week. We're gonna turn that in tomorrow, if I can, or at least have it a picture for you. But get out your notes, because again, still don't have books, but most of this stuff, I've kind of already led you into it, so you either should have prior notes or we're going to do something with it. So first, let me show you this fun little chart. Pause it up here. So we're going to talk about basically what we've been doing, and I've already led you into it. We're just going to get into a little more depth and add a couple more steps. But we're going to talk about product of powers, quotients of powers, power of a product, all that fun stuff. And it's essentially just like the bell work was, but again, we're going to take it a step further and add some extra things. First, let's talk about some vocab we got going on. So a radical expression is an expression that contains the radical symbol. Again, the radical symbol, that little squiggly line, that means something root, square root, cube root, whatever. That's the radical symbol. So if you ever hear me say the radical, I'm talking about that little squiggly line that's going over a, going over a number. In the radical expression, so that is the nth root of a, is how we would call it. Because usually, like when earlier, we had the cube root of 27. The nth root, that's just saying whatever number we put there, and then a is just we don't have a number there, so they're representing the variable. Hard to see. Okay, that's fine. It's just it's basically like cube root, but there's an n where the 3 would be. So it looks like, I'll just draw it out. Oh, there's Patrick. Nth root of a is what I'm saying. Oh, okay. I'll just explain it. Yeah, that's just, again, when I say nth root of a, we're saying there's some root we're finding of some number, and we're just going to use it like that to express, to get the vocab down. So in this case, the radicand is the number inside the radical. So like we had the cube root of 27, so 27 would be the radicand. N is called the index. So the index number is what root power we're talking about. So again, this one, the index for 3a was 3. The index for 3b was 4, because that was the power we needed to pay attention to. And it has to be greater than 1, because it wouldn't really make sense to have like a 0 power of something. It wouldn't do anything. But this one, it says the 5th root of 8. The index is 5, and the radicand is 8. And again, it reads as the 5th root of 8. And that's pretty much it. If it doesn't have an index, so if it doesn't have a number, like those have 3 and 4 as their index, what's it assumed to be? What root? If it's, yeah, square root. Go to Branson. So if you don't see a number, it's just automatically assumed the square root, and the power there is 2, or the index there is 2. All right, so if you ever hear me saying index, radicand, radical, That's what that means, so you're not ever lost there. But, sorry, what? Oh. My bad. You're right. Good job taking notes, because, again, you're not going to have this. And as you guys see with some of the assignments and quizzes I give you, sometimes I'll just give you a straight definition. So if you have the notes taken down, it should be pretty straightforward. I'll leave that up for one more second to get everybody in. And then when we're talking about exponents and the base, in this case, the base is 3. Said that a few times, but just so we always make sure when I'm talking about the base, the exponent, that's the exponent, and then the power, that's the number raised to the exponent. But mostly, as long as you know base and exponent, you'll always be able to follow along with me. All right, everybody good on this? So you don't have to copy all this down. If you guys are on Zoom, I would take a screenshot of this. For you guys, I'm gonna have all these meetings recorded, so you should be able to go back through if you need to. If you want to write some of this down, I would. I'll tell you some of the basic things. So like the first two, you should know those. We had those for bell work. That's the product of powers and the quotient of powers. So remember, like bases, you add them. Like that one in this case, it's 3 times, or 3 to the 4th times 3 squared equals 3 to the 4th plus 2. This is one of our bell works. Same thing here, except for this time it was dividing. I should do this so the Zoom people can see. 3 to the 4th divided by 3 squared. You subtract the exponents because it's a like base and it's dividing. Here's the other one. So we didn't cover this one. The power of a product. So in this case, it has 3 times 4 squared. So usually you could solve that out. You could just do 3 times 4, and that's 12. And then you would square that. 12 squared is 144. But there will be some instances where we can't multiply those two. Say again, if we have a variable or something else that we can't square exactly, you would instead do that first number squared times that second number squared, and then make it out to be what it is. And in this case, 9 times 16 is also going to be 144. So again, if they're multiplying and then the whole thing's squared, you square each individual number. All right, that's where we're at. Power of a power, we kind of reviewed that last time. If you have a power to the power, what do you do? What operation? Everybody, anybody? What do you do to the 2 exponents? Multiply, yes. So in this case, we have 3 to the 4th times 3 to the 2nd. So you do 3 to the 4th times 2, and you get 3 to the 8th. So if it's a power to a power, you multiply. Power raised to a power, what do you do again, everyone? Multiply. Power to a power, what do you do? Multiply. Woo, let's wake up a little. These are also 2 important ones we're going to spend a little more time on. Anything to the 0th power besides 0 is 1. So 5 to the 0 is 1. 100 to the 0th power is 1. 999,999 to the 0th power, still 1. Any number that's not 0, if it's raised to the 0 power, is 1. All right, that's always important. We'll see that a little bit we'll start combining these. And then the last one, negative exponents. If you have a negative exponent, you flip it from the numerator to the denominator and it becomes positive. So in this case, we have 4 cubed, or 4 to the negative 3rd. It would become 1 over 4 to the positive 3rd. So negative exponent, flip it from numerator to denominator. So it could be the opposite, like if we had 1 over 4 to the negative 3, you would just bring it up to the numerator and it becomes 4 to the positive 3. So I would definitely, for the ones we didn't do for bell work, that would be the most important to write down. And I skipped actually the power of a quotient. So this is fractions. It's a fraction. It's like you have 3 over 2 squared. You again just square both numbers. And that would become 3 squared over 2 squared. And you can solve it out if needed. All right. Any questions? Oh, David. Yes, David.
Can you hear me? Hello?
David.
Hello?
David, we can hear you, but I don't think he can.
Oh, there we go. My
Can you-
volume was down. Try it again.
So as far as power of production, so if I do, so like if you wanted me to add, like how we add the exponents with multiplying, if I had two of those, so like if I had 3 times 4 and they were in parentheses, and then I had like 2 times 4 and they were both to the second power, could I add those two exponents?
No, because hold on, let me write out what you're saying just so I can visualize it. So you're saying if we had 3 times 4 squared,
Right, and it equaled 12, and then I had another one that equaled 12, so like 6 times 2 to the second power.
oh yeah. So you could do that if you had 3 times 4 squared times 6 times 2 squared.
Yeah,
Yes, because in this case, you could just simplify the 3 times 4 to be 12 squared, and then same thing for 6 times 2 to be 12 squared, which would be 12 to the 4th, because you do the 12 squared times the 12 squared.
okay. And then
Yeah.
as far as the ones with the negative, I just put it in a, I just put one, I just put it over a fraction and change that exponent to a positive.
Yep, so if we had 4 to the negative 4th, that would be 1 over 4 to the now positive 4th, because this was essentially over 1, so we just put it in the denominator instead. Same thing if I had 1 over 3 to the negative 3, that would just become 3 to the positive 3, because it now went from the denominator to the numerator. We just kept it there.
Okay, alrighty.
Any others? Sorry, my volume was down, so if anybody else has a question before we move on. All right. Let's look at some examples. So let's just start with number 1. We're going to go through a couple of these, and then I'll give you guys some work to do. There should be an assignment posted right now, so it'll be due by the end of today, I believe. I'll double check that after class. But so when you guys get off Zoom, I'll tell you when. I won't keep you on here for an hour and a half. Go ahead and start on that assignment, and that'll be your independent work time. And then for you guys, I'll put it up on the board. And so you should have the work done, and then all you have to do is log into your Infinite Campus and then just submit the answers. And if you get it done in here, I should be able to go over it with you. But let's talk about number 1, some examples here. So it says, determine what real number 3.5 represents. Sorry, 3 to the 1/2. So in this case, when you have something raised to the half power, let's look at that. Let's use a different example than 3. Let's say we have 4 to the 1/2 power, and I multiplied it by 4 to the 1/2 power. Take a second to think what that would equal. So, what do you guys think? Well, 4 to the 1/2 times 4 to the 1/2, using what you know, what process would you do? What did Joe? Yep. Yeah, so for those who couldn't hear, Joe said since he knows the product of powers, he would do 4 to the 1/2 plus 1/2, and it would just become 4 to the 1 or just 4. Yeah, David.
No, I was just raising my hand to answer.
But yeah, so I'm assuming that's what you were going for too. We just add the powers. So when we talk about what real number 4 to the half power is, or anything to the half power, it would be the square root. So the square root of 4 is the same thing as 4 to the 1/2 power. And I demonstrated this because if I instead corrected those, instead of 4 to the 1/2 times 4 to the 1/2, and I used this rule, oh boy. Sorry, Zoom guys, I'll get it fixed in a second. Oh, no, my computer just crashed. That's good. You think school's getting money?
No, your personal.
Oh, I have it. I just don't. I was telling my buddy about how much I was playing. Oh, it's back. I was like, well, I've been playing this a lot, and I looked. It was like 6 hours in a week and a half. I was like, dang it, I'm old. I think that's a lot. Hey, man.
It's nothing.
I know. That's what I used to do in a day.
Yeah, easy.
All right, I think we're back. Woo, okay. Boom, we're back. So if I use this rule, knowing that the half power, let's instead of 4 to the 1/2 times 4 to the 1/2, let's do it as square roots. So it'd be square root of 4 times square root of 4. Well, square root of 4, that's just 2, right? So this would be 2 times 2, which still equals 4, just like we talked about earlier. So again, anything to the half power is the same thing as the square root. So if it's raised to the 1/2 power, you could instead write it as the square root of said number, and this is why it works. A little example to show how and why. All right. So let's look at the other ones. So this one has, it says, use that property to simplify the result of squaring 3 to the 1/2. Let's see what we would do there. So if I took 3 to the 1/2 power and squared it, well, in this case, it's a product to a product. What is it, Shyla? Yeah, so what would it be? 3 to the what power? What do you, so I have a product or an exponent raised to an exponent. What do we do for those again? You say multiply? Yeah, exactly. So Shyla says we multiply these, and that's right. It'd be 3 to the 1/2 times 2, and then 1/2 times 2, that's just 1. Multiply straight across, it'd be 2 over 2. And we could just simplify that to be 3 to the 1, or again, simplify it to just be 3. Now let's look at why we're looking at that. Because if we rewrote this as, instead of 3 to the 1/2 power, what could that be again? What, instead of to the 1/2 power? Anybody? The what of 3? Square root, thank you. One person paying attention. Square root of 3. So it'd be a square root of 3 squared, which we know, using our rules, that should just be 3, right? Even though square root of 3 is an irrational number, if we're squaring it, it cancels out. And it would just be 3. Let's look at like a tangible example as to why that could work. Square root of 4, go back to that. If I square that, we again know if something is square rooted and squared, it cancels out and should just be 4, right? Well, let's actually solve it. Since this is a rational number we can solve. What's square root of 4? Square root of 4, guys? 2, thank you. Square root of 4, what? Woo, all right. Square root of 4 is 2, and if we square that, again, we get 4. So that's why when something is square rooted and squared, just like how we talked about with the Pythagorean theorem, it cancels out. And again, this is how, then this is why. So if you ever see something square rooted and squared, it cancels out. Any questions so far? Still following me? Still waking up? When we talk about that, let's move on. So number 2, another example to go by. I know you can't see this entirely well, so I'll try to get it better. It says examine the methods below to see how the power of a power property can be used to define a to the m over n. So that's just some number raised to a fractional power. For any positive real number a and any integers m and n, they're just saying a is a positive number and the fraction is not some kind of weird square root irrational nonsense. So method 1, it says a to the m over n is the same thing as a to the 1 times n times m. Let me show you this. So if we have something raised to a fractional power, that is the same thing as saying 1 over the denominator times the numerator. It's just like what we did. Let me get that on screen. It's just like what we did up here, 3 to the 1/2 times 2. It's just going backwards. So it's something you probably already knew. It's just written out kind of differently with variables. And then that, if it's 1 over n, we have a raised to a fraction. We could say, just like up here, when we had something to the 1/2 power, it became a square root. Same thing, as long as there's a 1 in the numerator, you could instead write this as the nth root of a. That's what this would translate to. And then we would still have that m to the m power. So it would be nth root of a to the m power. So again, whatever the denominator is, the bottom number, if there's a 1 on top, we can make it that root. So let's look at an example. If I had 27 raised to the 1/3 power times 2, so it's a fraction, fractional exponent. I could instead turn this part into the 3rd root or the cube root of 27. And then I would still have to have it squared. And then we could actually solve that because the cube root of 27 would be 3. 3 squared is 9. The reason I show this is sometimes you can have fractional exponents that you're going to have to put into this form. So let's go a step backwards, and let's say we had 27 raised to the 2/3 power. Well, it doesn't seem like we can solve that, right? The fraction's not 1 over something. There's a 2 in the numerator, and we can't have a 2 in the numerator and do anything with it. But the equivalence to 2/3 is what I just wrote out there. I could write that as 27 to the 1/3 power times 2. Because these are two equivalences. One's raised to the 2/3, the other is just raised to the 1/3 and then times 2. I just drew it out. It's the same thing as if I said 6, well, that's the same thing as 2 times 3. I just wrote it differently. And my zooms, oh, there it is. Yeah, Patrick, question?
Yeah, what page are you on in the book?
Oh, sorry, I forgot some of you have books at home. I'm on page 13.
Okay, thank you.
Yes, sir. Yeah, we only got a couple books in, so some of the all online people got them first. That way they can actually have the reference material, and it's easier for them. Yeah, this is fun. Okay, so let's take a second breather and let my computer get fixed, and then we'll go back to this exciting curriculum.
How's your weekend?
Fun enough. Got a, yeah, I was very busy. Ouch. Yeah, as long as you keep your mask on. Played paintball for my wife's birthday. That was pretty fun.
Oh, wait. Paintball.
Yes, the ball of the paint.
Dang, I've never heard someone say that they've done that with their wife.
Oh yeah, it's great. I gave her, I have 2 guns. One's from like the year 2010 and one I just got this year. And so I used the old gun and I gave her my new gun to use. Okay, I was talking about paintball, guys. You guys came back in as soon as I was talking about guns. I used my gun. I gave my wife the other gun to shoot people with a paintball. Paintball is what we were doing. That was terrible timing. All right, so I think Zoom's back. Sorry, guys, it keeps going in and out, but we're doing our best.
Mr. Allen.
Yes.
So I don't know what it's doing on your computer, but the entire time, like, I could hear your entire conversation and stuff. So it's not freezing up on my end.
You guys aren't freezing?
No, not for me either.
Nope.
Mine's not
Yeah.
freezing either.
All right, that's good to know. So
Sir, you could call them no-no sticks instead of guns.
well,
No
paintball.
sticks.
All right. All right, remute yourself, guys. Now I know. I'm glad I didn't talk smack about you because you would have heard me. All right, so we're still on page 13. We're moving along. That was pretty much it. So again, if you have a fractional exponent, that's where we left off right there. 27 to the 2/3 power. We could instead write that as 27 to the 1/3 power times 2, and then we could actually solve it because again, if it has a fraction and the numerator is 1, whatever the denominator is becomes your root power. So it would be the cube root of 27, and then it's still being raised to the 2 power. And then again, if this was actually one we could solve, which we can, we would. If not, we wouldn't. We could show like a tangible reason why that works. Let's show one we know. Let's say we have 3 to the 2/2 power. Now again, I wouldn't really have to do anything for this. I just want to show you so you kind of get the gist of it. If it's 3 to the 2/2 power, again, I could rewrite that as a fraction. 3 to the 1/2 times 2. And then we know 3 to the 1/2 could be written as the square root of 3. Should have given myself more space here. And then it's still raised to the 2 power. But now I have a square root and a square. What's that going to do? If it's square rooted and squared, what happens? Cancels out. Thank you. So it just becomes 3, which is what we started with. 3 to the 2/2 is the same as 3 to the 1, which is just 3. Hey, it's trying its best, all right? Don't judge it. Someone called my 3 ugly. All right. So there's some good tangible examples of why and how that works. But let's look at some other stuff that's essentially going to be the focus is those powers over powers. And we'll do some expressions. So I want you guys to try this. Try this problem right here, and I'm on page 14 for those of you that have a book. Just try this in your notes. 9 to the 3/2 power. So try that out, 9 to the 3/2 power. So we have a fractional exponent. You want to rewrite it with a 1 in the numerator. So it should be similar to the one I just did with the 3s and the 1s and the 27. So I'll write the first step just in case you want to check it. Should be 9 to the 1/2 power times 3. Creates 1/2 times 3, the equivalence of 3/2. And now we have something raised to the 1/2 power. So I can write that as under the radical, and my index or my power I'm looking for is 2. So this would become the square root of 9 raised to the 3rd power, because I just turned this to the square root of 9 and kept it raised to the 3rd power. Square root of 9 you can actually solve for. It would be 3. Keep that 3rd power, 3 cubed, to get my final answer of 27. Any questions on that? All right. Let's look at another one. Well, let's get, no, we'll do this one first, and then we'll get fancy after this. So we have 8 to the 2/3 power. Try that one out in your notes as well. So again, you want to rewrite it with a 1 in the numerator. And then if you can change it, well, if it has a 1 in the numerator and it has an exponent, you should be able to change it under a radical. And then if you're able to solve the radical, solve it, and then raise it to whatever power it's telling you to. So your first step should have been 8 to the 1/3 power times 2. And then 8 to the 1/3 power, I can put that as instead the cube root of 8, because my denominator becomes my index there. I still have to have it squared. Now be careful with this one because it's a cube root and it's squared, so it does not cancel out. Because the index and the exponent are different. If it was the square root and the square, that would cancel out, and we looked into why that was. And then I could actually solve this cube root of 8. That would become 2, because 2 times 2 times 2 is 8. It's still being squared. And then 2 squared, big brain, 2 times 2 is 4. Yes, Seth?
So whatever the denominator is, in like a fraction, would that be how many times, or is it a cube root every time?
Yeah, so it's whatever the denominator is. So Seth asked where we're getting this index from, and it's always the denominator. So we could look at another example. Let's say instead it was 8 to the 3/4 power. So this one I'll just do for you guys. It would become 8 to the 1/4 times 3. Sorry, I just realized I messed that up. 16 to the 3/4 is what I meant to say. That would become 16 to the 1/4. Golly, 1/4 times 3. And so 16 to the 1/4 power would become the 4th root of 16 cubed. And now the 4th root to the 16 we could actually solve, because that would become 2, since 2 times 2 times 2 times 2 is 16 cubed 8. Yeah, so good question, Seth. Anytime, whatever your denominator is, that becomes the root you're looking for. Okay, now let's get a little fancy. Let's say we have, and this is on page 14 for the, have a book, 4 to the negative 3/2 power. So using what you know, see if you can figure that one out. So it's the same as the other ones. There's just that one step you got to take before you can solve it. So I'll write out the first step in case you're stuck. So you really have 2 options for your first step here, but generally you're gonna wanna always turn that exponent positive first. So this would become 1 over 4 to the positive 3/2 power. Now technically you could have done this step first, where you write it out and get it as a fraction. That's 1 over 2 times 3. But generally, first step, you're going to want to turn it positive and then worry about all the other fun stuff. So we go 4 to the negative 3/2. all I did was flip that. Since it's a whole number, it's in the numerator. I put it in the denominator, and I changed the exponent to be positive. And now we follow the rest of the rules. It would become 1 over 4 to the 1/2 power times 3. And again, we can exact same rules, it's just in the denominator. So don't worry about it being a fraction and being weird. Just take the denominator and solve that out and just put it under 1 after everything's said and done. So this will become 1 over square root of 4 cubed, which would be 1 over square root of 4 is 2 cubed. To get our final answer, write it down here, of 1 over 2 cubed would be 8. So this is where, again, it gets a little different. You can have negative fractional exponents, but just follow the same rules you know. Just take it, switch it from the denominator to the numerator, whichever one it's in. Exponent becomes positive. Follow your rules, get a 1 in the numerator, solve it out. We're all good. Any questions so far? All right. Let's look at one more example, then I think I'll let you guys work for a bit. No, we got a couple more. This is fun. So this is on page 14, last example there. I'm going to need some good room for this. So we've got 64 to the 2/3 power minus 125 to the 1/3 power. So at first it looks like you might not be able to solve for this because, I mean, you can't really take a number with an exponent that's a fraction and do anything unless we solve it out. So let's use the rules we know, solve if we can, and then we'll figure it out after that. 64 to the 2/3 power, I'm going to instead write that as 64 to the 1/3 times 2 minus 125 can just stay 125 to the 1/3, or you could have already done the third root or cube root. This right here is going to become the cube root of 64. I still have that 2 hanging out, so it's still got to be squared. Then I'm going to subtract cube root of 125 because it was raised to the 1/3 power. 1 was in my numerator. My denominator became my power, or my index. Can actually solve both of these. Cube root of 64, that would be 4. 4 times 4 is 16 times 4 is 64. Still got that squared hanging out, so we're going to still have it down there. Cube root of 125 would actually be 5, because 5 times 5 is 25, times 5 is 125. And then just solve it out. 16 minus 5 is 11. All right. Now this is where it gets fun, I think. We're on page 15 now. Oh, yeah, Patrick.
For when you had 4 to the second power, where did that exponent come from? Like,
So since we
where did
have
you?
64 to the 2/3, we put it as 64 to the 1/3 times 2. And then we got the cube root of 64, since it was a fractional exponent with a 1 in the numerator. We just made our index our denominator. And then cube root of 64 would become 4, because 4 times 4 times 4 is 64. And then,
Oh, okay, I get it.
since there was still a 2 in the exponent, we still had to keep that squared there.
Oh, okay.
All right, good question. Anybody else before we move on? All right. So this, we're on page, let's say 15. I'll just write these out, obviously. Let's say we have this one, 64y squared raised to the 3/2 power. Looks a little funky, right? But if you know your rules, we'll just follow the rules here. So I'll do this one step at a time. Since we have something in parentheses, and then we have an exponent raising the entire parentheses, remember, we can put that exponent to both of these powers, and we'll multiply them. So 64 would become 64 to the 3/2 power, and we could say times y squared times 3/2 in the exponents. Because all I did was, let's assume this is essentially 64 to the 1 power, and I just multiplied this exponent by these exponents. So 64 to the 1, well, 1 times 3/2 is 1, so it becomes 64 to the 3/2 power, times y was being squared, so since it's an exponent to an exponent, remember we multiply, so it became 2 times 3 to the 3/2. What did I just say? 2 times 3/2. Can't speak today. Now we'll solve this out. So 64 to the 3/2 power, we would instead write that as 64 to the 1/2 times 3 power, still times y to the 6/2, because 2 times 3 over 2 would become 6 over 2. Now with this one, 64 to the 1/2 power, that becomes square root of 64, because it has a 1 in the numerator, 2 is in the denominator, so that becomes my index. Remember, if it's not written there, it's implied to be a 2. That still needs to be cubed, because there was still a 3 hanging out there. Now y to the 6/2 power, I don't really have to do anything special to that. Since it's 6/2, I can just write that as y cubed. I'm going a little bit off the book here, but not really. Square root of 64, what's that? Anybody? 8, yeah. So that just becomes 8 cubed times y cubed. Remember, if it's a variable, you can just write it out, and it's assumed to multiply. You don't have to write the multiplication symbol. And 8 cubed, if you actually do that out, it's like 512. Yes, 512. And then we can't do anything with y cubed. So our final answer here, we would leave it as 512 y cubed. How are we doing, guys? Overloaded yet? A little bit? So I think we'll cut this off here, and I'll give you guys some time to work, and we'll maybe review a little bit more on Wednesday about this. Or for those of you that are in here second period tomorrow, we'll spend some more time practicing these. So if you guys are on Zoom, you're welcome to leave. I'm actually about to stop the Zoom. Well, I'll leave it on for a little bit if you guys want to work on the assignment and ask questions, but if you want to leave to look at the assignment that's posted on Infinite Campus, you can go ahead and do that now and just pop in if you have questions or anything. For you guys, I'll pull this up so you can start on it now, and then you can hopefully when you get home you'll have all the answers, and you should just have to click the answers. If my computer works. Oh, there it goes. There it goes.
Have a good day, sir.
You too, Patrick. Good to kind of see you.
Are we allowed to bring our own laptops into this class?
I don't see why not. I'll have to double check, make sure that's fine, but
Because I know like other classes are allowed to, I just didn't know about.
yeah, for this one, since you're gonna be doing the work virtually, you may as well have a, yeah, that way at the end of class, you can just turn it on and work on it. So yeah, that should be fine. I'll double check to make sure, but here's the thing, maybe, if it'll load. Jeez. All right. Can I see it? There it goes. So I froze it on there just in case when I pull it up, it has all the answers. Yes, ma'am. Bazo? Don't have him. He should be, if he's in math right now, he'll be in voices, but. Welcome.
That kid's smart.
Okay, looks like it's good now. So I'll just write these down and you guys can get them afterwards because apparently I can't show it without the answers, so bear with me.
You could freeze it and then block out the answers.
I can't really block out the answers.
Like on the whiteboard. Get an expo and
Probably not. It's fine. It's only 3 questions actually. I thought I did more, but I guess I was feeling nice when I made this. Do, do, do.
olden days, sir. On the computers.
Yeah, I mean, I'm pretty sure this computer is from the olden days. So those would be the ones you have tonight. So go ahead and start on them here. And then, yeah, you should have the answers ready to go. You'll be working on these on your own. We have 30 minutes of class left, so if you get done with these early, you're more than welcome to take a second to review, ask any questions maybe. So number 1 should be pretty straightforward, or at least very similar to the notes you saw. Number 2, a little different. Again, it's just remember your first step. From that, should only be 1 or 2 more steps after that. And number 3, that one's going to be weird. We actually didn't cover that. So I'll give you an example to be similar. Let's say we have, 1/3 to the -5th power. So my fraction, it would become 1/1/3 to the 5th power. But you can't really do that. That doesn't make any sense. You got 1/1/3. It's a lot. But let's remember our rules. If you have a fraction divided by a fraction, you multiply by its reciprocal. So what I would do is take 1 over 1, because that's my numerator technically, and multiply it by the reciprocal of my denominator, so my bottom flipped, 3 over 1, and this would actually just become 3, and then it's still to the 5th power. Because if you think about it, I'm doing 1 divided by 1/3. How many times would 1/3 go into 1? It'd be 3 times. Yeah. It's like if you had 1 divided by 1/4. Or that'd be $1 divided by 4 quarters. There's 4 quarters in $1. So use that to determine that, and it should come out. All of these should be solved out. So you shouldn't be left with any square roots or any exponents or anything like that. Yeah, Seth, what's up?
So with like number 1,
Yes.
I got 4 and 1/2 times 5, but I completely forgot like
What to go from there? Yeah, so you got the first step, but now you've got a number raised to the 1/2 power, just like we had. Yeah, it's like here, we solved this out to be 9 to the 1/2 times 3, and since it's raised to the 1/2, that becomes the square root of 9 instead.
so I would do the square root of the square root of 4.
Yep, raised to whatever power you have left over.
Okay, and then just multiply it.
Yep, well, yeah, so solve square root of 4, and then after you solve square root of 4, raise it to the 5th power. That should be your answer. Yeah. Mm-hmm. Yep. So since it's a, well, so that one you don't have to multiply or change your exponent at all, but to change it positive, we have, this is technically 25 over 1, right? 25 to the negative 1/2 power over 1, we could say. So to get your exponent to be positive, you got to put it in the denominator instead. So like I think we did one example. I can show you one that's similar. If I had, say, 16 to the negative 1/2, I could instead make that 1 over 16 to the positive 1/2. And then just follow the same rules. It's raised to the 1/2 power. So instead, I would say 1 over square root of 16, since it's raised to the 1/2 power. And then this would just be 1/4. All right. Aiden, do you have any questions, or did you just walk away and you weren't paying attention, so you're still in the room? Yeah, I figured it was that one. All right, Aiden, I'm ending the Zoom, so I don't know where you are in your house, but oh, he's gone. Maybe he actually was there. Ah, that's me. Oh.